Every 12 months, a familiar ritual takes over your feet. A darkened auditorium, a glowing screen, a CEO holding a slab of glass and polished metal. The messaging across the mainstream media sphere is always identical. The device you held yesterday is now inadequate. But if you step outside the hype cycle and look at the physical silicon, an uncomfortable truth emerges. For the 90% of human workflows, the hardware won years ago. To understand why the baseline flatlined, we have to look at the mathematical decoupling of hardware capacity and human biology. Human beings read, type, and process information at a fixed static speed. A typist in 1983 entering text into an Apple IIe experienced a system latency of roughly 30 milliseconds. The machine responded almost instantly to human muscle movement because the operating system spoke directly to the bare metal. Fast forward to the present day, a modern flagship laptop running an abstraction-heavy desktop environment frequently clocks in at 100 milliseconds of input latency for the exact same task. We have multiplied transistor count by billions, yet the basic loop of human to computer interaction has actually degraded. Look at the data tracking open office against Crider's law across a 6-year development cycle. Hard drive capacity multiplied by a staggering 100 times. Yet, the storage and memory footprints of the software humans actually used to type documents barely doubled. The silicon outpaced human utility almost immediately. For the vast majority of personal, administrative, and development tasks, consumer chips reached operational sufficiency over a decade ago. When you're buying a modern processor today, you are not buying a speed that your applications are begging for. You are buying raw overhead. You are paying for a massive engine that will spend 90% of its lifespan completely idling during your daily workflows. The industry hit a wall, not of capability but of necessity. The democratization of computing has plateaued. A premium processor from several generations ago handles encrypted messaging, web completion, and high-fidelity audio with zero friction. The massive vertical leaps in processing power that defined the early era of computing have flattened into minor iterative bumps. So, how does a multi-trillion-dollar industry force a market to buy what it doesn't actually need? They manufacture an expiration date. They do this through three distinct pillars: artificial segmentation, the sabotage of repair, and the weaponization of security. If you want proof that this is a choice, not a technical limitation, look at the primary battlefield for modern digital creators: the hybrid camera. When a company artificially limits a smartphone, they can always blame security concerns. But a camera doesn't hold your banking passwords. Yet, manufacturers will use exact same image sensor and processing silicon across multiple tiers of cameras and intentionally write firmware that limits the cheaper hardware. A hybrid body could easily output 10-bit color, record past an arbitrary 30-minute limit, or utilize advanced autofocus. But the line of code acts as a digital bouncer, demanding an extra $2,000 for a different plastic badge. It is pure naked market segmentation. This exact model of software castration scales down directly into the palm of your hand. To bypass skyrocketing retail prices, savvy users turn to refurbished devices. The silicon is pristine, but they are subjected to a digital gatekeeper, a permanently locked bootloader. When a manufacturer decides a phone model has reached its end of life, they halt updates. Simultaneously, they lock the system gate, preventing the open source community from patching the kernel for you. The code reads bootloader unlock allowed no. Your ownership of the physical machine is overridden by a line of code. To understand how deeply we have regressed in software efficiency, we have to examine the structural foundation of the programs we run. If you look at major enterprise assignment from a decade ago, for example, a highly robust air ticket reservation system written in 2014. It was built using native compiled languages like C++. The code spoke almost directly to the microarchitecture of the CPU. It was mathematically disciplined, managing memory registers by hand and moving data with minimal overhead. The software didn't need a multi-core gigahertz processor to run smoothly. It could execute on nominal hardware because there was no middleman. Today, that exact same ticketing system or email client or chat application is wrapped in layers of modern web frameworks, bloated runtime environments, non-negotiable background telemetry. The fundamental task, rendering text or processing a local database transaction, requires the exact same mathematical logic as it did 12 years ago. Yet, modern software demands an octa-core mobile processor just to chew through the unoptimized code bloat layered on top of it. This isn't a software evolution, it is architectural laziness hidden behind exponential silicon gains. The industry is trapped in a compounding loop. Programmers write increasingly inefficient code because they assume the hardware will get faster, and manufacturers build faster hardware just to compensate for the increasingly inefficient code. When your phone begins to stutter after 3 years, the silicon isn't wearing out. The software is simply growing too heavy for the physical container it was designed to inhabit. If you do manage to break past the corporate lock and install a clean, community-driven OS to extend the life of your device, the ecosystem retaliates. You open WhatsApp and warning flashes, device insecure. You open your banking app and it refuses to load. The tech media sphere constantly echoes the corporate warning. Unpatched software is a security hazard. But for disciplined user who disables media auto downloads, strips background carrier telemetry, and manage their network parameters, the device remains a secure fortress. The hardwired security enclaves on the chip do not magically degrade over time. The corporation simply uses security as a psychological compliance tool. The weaponization of security functions as the ultimate psychological compliance tool because it relies on asymmetric information. The average user cannot audit a closed source operating system kernel. When a dialog box flashes in bold red text warning that your system is exposed, the natural human reaction is fear. This fear is systematically cultivated to mask market saturation. If you look at the physical architecture of a modern system on a chip, the hardware level security enclaves, the isolated silicon blocks that handle cryptographic keys and secure boot operations, are permanent. They do not decay, they do not lose their structural integrity after 36 months. A device running a fully patched, community-audited Linux kernel or a hardened open-source Android distribution is often vastly more secure than a stock factory operating system packed with proprietary carrier telemetry and unmonitored background diagnostic hooks. But a secure machine that you fully control is a financial dead end for the original equipment manufacturer. By framing corporate software abandonment as an existential security crisis, they transform a routine corporate lifestyle policy into a moral imperative to upgrade. They force you to discard a perfectly functioning machine under the guise of protecting you from it. This digital containment zone is not limited to the pocket-sized device you carry. The exact same corporate playbook using code to render perfectly functional silicon obsolete is currently being executed on a massive macroeconomic scale. It is happening to the machine sitting right on your desk. In 2015, Microsoft stated that Windows 10 would be the definitive final version of the operating system. In 2021, that directive was abandoned with the launch of Windows 11, which instituted rigid hardware barriers around CPU generations. This single decision systematically condemned an estimated 240 million functional computers to early obsolescence. These are quad-core machines with ample RAM that comfortably process real-world administrative and development tasks. Now, the goalposts are shifting again. To access the full breadth of the modern Copilot experience, the mainstream narrative states you must possess a neural processing unit capable of 40 trillion operations per second. Hardware purchased a mere 36 months ago is repositioned as a legacy burden. When you look beneath the marketing veneer of these modern operating system cutoffs, the technical justification completely disintegrates. Millions of the machines legally owned by these software mandates are enterprise-grade workhorses. There are quad-core, hexacore, and octa-core processors sitting on massive memory architectures. They are entirely capable of compiling complex code, rendering vector graphics, and executing localized databases without a microsecond of hesitation. The restriction isn't based on raw processing muscle, it is an instruction set architecture lockout. By mandating hyper-specific cryptographic hardware modules like Trusted Platform Module 2.0 or enforcing strict generation cutoffs for processor architectures, corporations are drawing an arbitrary line in the sand. Silicon that could comfortably handle real-world engineering, administrative, and creative workflows for another decade is transformed into a legal liability for corporate IT departments. Now, this cycle is accelerating with the introduction of dedicated neural processing units. The consumer is told that without a dedicated silicon block capable of 40 trillion operations per second. Their machine cannot process the next generation of computing. But an NPU is not a magical accelerator. It is simply an array of specialized matrix multiplication engines. The underlying CPU and GPU. You already own a perfectly capable of executing these exact same mathematical algorithms. They simply do it across standard parallel pipelines by fabricating a narrative that tasks must run on specialized, newly purchased silicon. The industry manufactures a synthetic performance crisis to clear out inventory and reset the consumer upgrade clock. Why the aggressive push toward these AI integrated interfaces? Because modern operating systems are transitioning from local productivity platforms into continuous data extraction engines. Modern desktop systems mandate baseline telemetry data collection. They frame this collection as diagnostic tracking essential for system health. But in reality, this massive influx of user behavior metrics fuels targeted advertising networks and builds the data model required to train corporate generative AI. Your older hardware isn't being pushed aside because it lacks math skills to compute. It's being pushed aside because it doesn't feed the data engine efficiently enough. This shift represents a fundamental transformation in the economics of consumer technology. Local computing is a finite profit loop. You buy a perpetual license for an operating system. You install your tools, and the commercial relationship ends. The manufacturer cannot continuously monetize a machine that sits quietly on your desk performing local tasks. But a telemetry-heavy, AI-integrated OS transforms your local processor into a permanent revenue node. When your machine is constantly logging your context, monitoring your application state, and tracking your behavioral patterns, it requires an immense amount of background bandwidth and continuous instruction cycles just to maintain its corporate connection. Your older computer is discarded not because it is too weak to run a word processor, but because it represents an unprofitable user state. It is an island of local autonomy in an ecosystem built entirely on centralized data extraction. The industry must render that local machine obsolete, because if you are allowed to stay there, you are a consumer who cannot be continuously harvested. To fully understand how artificially shortened our upgrade cycles are, we have to look at the enthusiasts who refuse to let hardware die. The absolute proof that silicon is designed to last a lifetime exists in the hardware modding community. Take classic gaming hardware from previous generations. A machine running intense, graphically demanding software for over a decade doesn't just expire. When performance dips, it isn't the silicon failing, it is physical maintenance being ignored. By simply opening the chassis, cleaning the logic board, replacing degraded thermal materials with fresh thermal paste, and bypassing artificial software locks, The hardware is completely revitalized. It runs just as efficiently as the day it was manufactured. Let's analyze the cold physical reality of hardware aging. Silicon is a crystalline structure. Barring an catastrophic electrical surge, a microprocessor does not wear out like a mechanical gear. It does not suffer from friction. Its lifespan is governed almost entirely by thermal dynamics and electromigration. When an older piece of hardware begins to stutter, crash, or drop frames under load, the mainstream consumer narrative suggests the machine is simply getting old. But this is a fundamental misunderstanding of physics. Look at the hardware efficiency data tracking compute scaling across multi-layered systems. As computational load intensifies, hardware efficiency hits a steep, rigid physical plateau governed by thermal resistance. When you open a legacy console or an older performance laptop that has been running for decades, the physical breakdown is never the chip itself. It is the interface material. The factory installed thermal compound designed to bridge the micro gaps between the silicon die and the copper heatsink degrades over time. It turns into brittle, crusty, calcified insulator. Instead of conducting heat away from the processor, it traps it. The silicon, detecting a critical thermal threshold, automatically drops its voltage and scales down its clock frequency to protect itself from structural failure. It throttles. The performance dip you experience is a protective software loop, not a dead chip. By simply removing the chassis screws, cleaning the logic board with isopropyl alcohol, scraping away the dead material, and applying a fresh drop of high-grade thermal paste, you drop the thermal resistance instantly. The processor scales back up to its maximum clock speed. It executes its instructions flawlessly. The physical engine is entirely intact. It simply required ownership level maintenance. But tech conglomerates actively sabotage this physical longevity through parts pairing, linking the digital serial number of a screen or battery to the logic board. If you try to perform basic maintenance, the software intentionally breaks biometric sensors or floods your screen with warnings. They do not want you maintaining the engine. They want you to buy a new car. But this corporate lockstep has a critical vulnerability. When you strip away the proprietary software layer, you discover the underlying hardware remains an incredibly resilient machine. Enter the Linux solution. Linux does not answer to shareholder growth targets. It views an older processor not as a depreciating asset but as an array of processing cores waiting for efficient execution terms. By swapping out a telemetry heavy OS for a lean Linux architecture, older computers are instantly revitalized. Idle memory utilization drops by half. Background tracking drops to zero. A machine destined for landfill transforms instantly into a fast, secure workstation. The game changes the moment you alter the instruction you feed to the silicon. The ultimate validation of this approach is found in a real-world creative execution. Take a machine that arbitrary Windows 11 cutoff defines as a e-waste. Something like a few generations old AMD Ryzen laptop. According to the mainstream review cycle, a computer like this is obsolete, incapable of participating in the modern creative workflow. When you remove the telemetry layer and hand the silicon to a lean, unbloated Linux architecture, you unlock the raw physical capacity of the machine. The exact same hardware will flawlessly run professional open source creative application like Krita. It can handle massive digital canvases, render complex multi-layer storyboards, and animate fully rigged characters with absolute real-time stability. The silicon doesn't care about market validation or corporate fiscal quarters. It executes mathematical operations. When you strip away the predatory software layers designed to force an artificial upgrade cycle, you realize that the machine you bought years ago is still an absolute powerhouse. It doesn't need to be replaced. It just needs an operating system that respects its engineering. The mainstream media sphere, powered by corporate review, access, and continuous marketing cycles, will continue to argue that hardware without the latest NPU chip or automated software subscription tiers is a functional failure. But hardware is an engine. Its ultimate lifespan is dictated by how it is managed, how it is optimized, and who sits behind the controls. When you develop operational discipline, when you curate your data parameters, maintain your thermals, fight for the right to repair, and look towards open source options, you transition from a passive consumer into something entirely different. You become a custodian of your own technology. We do not always need the latest and greatest gadget. We simply need to protect our right to use, repair, and truly own the magnificent machines we already have. Remember, in a world shaped by technology, you hold the controls. Stay analytical, stay autonomous, and as always, stay curious. See you in the next one. Thank you for watching.